Hi all, myself Sudha, working as Assistant Professor, Department of Computer Science Engineering, S.A.E.C Engineering College. Today we are going to discuss about gate questions on the topic trees. So in the tree, we are going to discuss about AVL trees. So first, before getting into the trees, we will discuss what is data structure. So data structure, we are going to organize the data in the computer in an efficient manner. So we can organize the data in the computer by using two types of data structures, linear data structure, non-linear data structure. Data structures can be classified into LDS, NLDS. Linear data structures, non-linear data structures. In the linear data structures, we will organize the data in the form of stack, queue and list. So list, we will represent the data. So linear data structure, what do you mean by linear data structure? We will organize our data in a linear, that is in the form of sequence. So one after another we are going to store our data. So only the representation is different when you compare all these concepts. So list, we will represent the data like this. In the stack, we will represent the data in the form of like this. And in the queue, we will represent in the form of like this. So here we will use the two pointers, rear and front pointers. Here we will be using the top pointer, and here we will represent our data in array based or linked list based implementation. So this is the way we are going to organize the data in a linear data structure. When you come to the non-linear data structure, we can organize our data in the form of trees and graph. So both we are going to follow the hierarchical relationship. So hierarchical relationship will be having, when you come to the tree, it is having parent-child relationship. So we will be organizing data in a hierarchical form like this, and all the data will have a relationship with one and another. When you come to the graph, we will organize the data in the form of like this. And in the graph also, we will be having a relationship between the vertices, one vertices to the other vertices. Here we will be calling all these elements which is stored in this circle, we will be calling as a node. And here we will be calling as a vertices. So this is the simple introduction about your data structure. Now we are going to see about the trees. So trees comes under the concept of non-linear data structure, and we will be having different types of trees. We can organize our data, we can store our data in the computer that can be efficiently used. So what tree we are going to discuss today is a AVL tree. So what is a AVL tree? Why do we need a AVL tree? So AVL tree, we will be having a tree called, BST. So from the BST only we are going to derive a AVL tree. So what is the BST? So BST, it will follow the concept of BT. And it will take the property of BT and it has its own property. So what is the BT property? So in the BT property, the nodes in the tree have at most 2 children. That is, the node can have 0 children, 1 children and at most 2 children. So it will take the BST take the property of BT and its own property, that is, when you have a node, when you are going to create a child for the node, the child node in the left side is less than and the child node in the right side is greater than. So the BST will hold the two property. The one property that comes from your binary tree and its own property, that is left child is less than value when you compare to the parent and the right child is greater value when compared to the parent. Then why do we need the AVL tree? We have a BT, we have a BST. From the BST we are going to AVL tree. So why do we need the AVL tree? So AVL tree will be calling the tree of AVL tree is a height balance. So we are going to balance our height of the BST. So when the height will not be balanced, when the tree, for example, I am going to construct binary search tree for the following elements. For example, now I will take the first element as a root node 1. Now I will insert this next element, second element is 2. When I compare the 2 with 1, it is greater. So I will always insert at the right side. Now I will insert the next element. The next element is 3. When I compare with the root node, it is greater. So come to the right side. Right side already one element is there. Now I am going to compare that element with the element which is already there in the tree. Now it is also greater. So it will come to 3. Likewise, we need to compare the elements to insert in the binary search tree. So when you compare the element 4, it will obviously come to this position. When you compare the element 5, again it comes to the position 5. So when you calculate the height of this particular tree is 1, 2, 3, 4. That is 4. Now we'll be calling this type of tree is a right-skewed binary tree. Right-skewed binary search tree. Likewise, when you have the tree like this 10, 9, 8, 7, 6. When you draw like this, then the tree will be growing only in the left side. Now we'll be calling this tree as a left skew binary tree. So when the tree is growing only at the right side, only at the left side, then it will give the issue of complexity in the binary search tree. That is, when you are searching any element in the binary search tree, it will take the time consuming process. You want to reduce that one, we are going for the AVL tree. So the main thing of doing this AVL tree is you are going to balance the height of the binary search tree. So how you will balance the height of the binary search tree? You will calculate the balance factor. So what is the balance factor? So balance factor you are going to calculate for each and every node in the binary search tree. So we have a formula for that. This is a formula. You are going to consider the height of the left subtree and the height of the right subtree. For example, you want to calculate the balance factor for this node. There is no left subtree and right subtree. So 0 minus 0, it is 0. When you calculate for this having only the left, so 1 minus no right subtree, so 1 minus 0, it is 1. Likewise, we will calculate the balance factor for all the nodes. So when you will be knowing that the given tree is unbalanced. When the balance factor is not satisfied with these values minus 1, 0 and plus 1, then the tree is unbalanced. So when the tree is unbalanced, you want to do something to become your tree into the balanced binary search tree. So if you want to do that, you will perform rotations. So rotations is come into the picture. So rotations is come into the picture if you want to balance your binary search tree. So what are the types of rotations we have? We can perform two types of rotation, that is single rotation and double rotation. When it is single rotation, we can perform again two types of rotation, LL rotation and RR rotation. Double rotation we will perform LR rotation and RL rotation. That is, here the left rotation, LL means left rotation, right rotation, then left right rotation and right left rotation. So when the LL you will be performing, when the new node is inserted to the left subtree of the critical node. When you are inserting any new node that is in the left side, when after inserting the new node in the left side, the node becomes the parent of the particular node or any node in the left will becomes critical, then you will perform the LL rotation. When you go for the RR rotation, the new node going to be inserted at the right side subtree of the given AVL tree. Then ILL rotation, so LR rotation will be having this. So we'll be having the node like this. Now this is your left, and it will perform in the right. Now we will perform the LR rotation. Next RL rotation, the new node going to be inserted at the left subtree of the right subtree of critical node. That is, you will be having the node. This is the already existing node. The existing node are available in the right. Now you are going to insert the new node in the left. Then it will be giving the node becomes here as a critical node. When the node becomes here as a critical node, then you are going to perform the RL rotation. This is an example. So now the node which is there here is 5 and 3. So 5 and 3, it is a left. So it is the left. Now I am going to insert the new node called 2. I am going to insert at the left. So how I will be I will be notifying that the particular node is critical. So first you have to calculate the balance factor. So now the balance factor for this node 2 is 0. And this node, the left subtree 1 minus right subtree, there is no right subtree, so 0, it is 1. Now I am calculating the balance factor for the node 5. The left subtree 1, 2. So 2 minus, and the right subtree, no right subtree, it is 0. 2 minus 0, it is 2. Now, which is the critical node? The node which is having the factors without your plus 1, minus 1, 0. Now, the 2 is having the balance factor of 0. So, it is okay. No critical node. Now, the balance factor of the node 3 is 1. It is not the critical node. Now, the balance factor of the node 5 is 2. Now, this is your critical node. Then, you are going to apply the rotation. You are going to find the rotation. What type of rotation it is? So, it is L. So, you are going to apply the LL rotation. LL rotation means you are going to be rotate in the right. So, when you rotate in the right, you will pull this element here and it will go here. Along with this, the 2 is also goes with the 3. So, now this is the result of LL rotation. You are going to perform the LL rotation like this. Next one is your RR rotation. So, RR rotation, same, you are going to find the balance factor first. So, the balance factor of the node is here, since it is a leaf node, so there is no left subtree, right subtree, so it is 0. Next, when you come to the next node, next level of the node, here there is no left subtree, so 0 minus, only one right subtree, so 0 minus 1, it is minus 1. When you come to this node, there is no left, so 0 minus, what is the height of the right subtree? 1, 2. So maximum height you are going to find out. So 1, 2, so 0 minus 2, it is minus 2. So now which node is a critical node? Obviously the 3 is a critical node. So first you are going to find out what type of rotation you are going to apply to become the unbalanced to balanced binary search tree. So it is a RR rotation. Why it is a RR rotation? Now the new node inserted here is 7. In the which side the new node is inserted? The new node is inserted in the right side of the right subtree. So it is a RR rotation. So you are going to apply the RR rotation. If it is a RR rotation, you are going to change the tree in this form. So 3 will come here, 5 will go here, along with that 7 will also go. So this is the result of your right rotation. Next one is your LR rotation. So LR rotation, first you are going to find out the balance factor. The balance factor of all the nodes. So here, since it is a leaf node, the balance factor is 0. And here, no left. So 0 minus, only one right. So 0 minus 1, minus 1. When you compare this, there is a no right subtree. We have only the left subtree. So you are going to find out the maximum depth or height. So here the maximum depth or height is 2. So 2 minus 0, it is 2. So the critical node is this. So how you will be changing here? You will be changing first, you will be applying 5, 4 and then 3. You will be doing like this and then you will pull in the right side. So 4, 3 and then 5. So since this is your resultant. Next one is your right RL rotation. So RL rotation, first in any AVL tree or any balanced binary search tree, first you are going to find out the balance factor. By calculating the balance factor only, you can able to find out that the given AVL tree is a balanced or not. So here the balance factor is 0. When you calculate this, the balance factor is 1. when you calculate this, 0 minus 2, it is minus 2. So obviously this is your critical node. You are going to apply the rotation, you are going to find out the rotation. So which is the new node inserted to this AVL tree? That is 4. In which side it is inserted? It is inserted in the left. So L. So when you come to the next critical node, when you are going with the critical node, the path or the way you want to go and you find out the critical node is the node which is having the balance factor not comes under the form of +1, -1 and 0. So now this is the path, so RL rotation. So when you apply the RL rotation, so first you are going to pull this, so 3 and then 4 and then 5. So after you are going to apply the rotation in the left. So when you apply the rotation, you will be getting finally 4, 3 and 5. So this is your result. This is what you are going to apply the RL rotation. So now we discussed about 4 rotation, single 2 rotation and double 2 rotation. So whenever you want to convert the unbalanced binary search tree into the balanced binary search tree, then you will be applying all these rotations. So now this is an example. This is a tree already there. So we are going to insert the new element called 18. So 18, first you are going to start comparing with the root node. 18 which is less than your root node. So come to the left. Now the left is already available with some other node. Again we need to compare. So now compare 18 with 36. So that 18 is less than. So come to the left. 27 is the node is already available. Again you compare. So 18 is less than 27. So we inserted at the left of the 27. Now whenever you are doing the insertion in the balanced binary search tree, that is the AVL tree, always you are going to calculate the balance factor. Now calculate the balance factor. So since it is a leaf node, there is no left subtree and right subtree. So the balance factor of the leaf node is always 0. So you put 0 for all the leaf nodes. Then come to the next level. So in the next level, is there only the left subtree? So it is 1. Now come to the next level. Here we are having left height is 2. So left height is 2. So 2 minus right is 1. So 2 minus 1 is 1. When you come to this, left 1, 2, 3. So 3 minus the right 1. So 3 minus 1, it is 2. Since it is a leaf node, 63 is a leaf node, it is 0. Now which node is critical now? You want to check all the balance factors. So here 0 not critical, 1 not critical, 0 not critical, this is also not critical, this is also not critical. So the critical node is 45. Now, so once you find out the node which is having the balance factor is not lies from +1, -1 or 0, then you are going to apply the rotation. First you are going to find out what type of rotation. What type of rotation we are going to apply to that to become the node to the normal node. So what type of rotation it is? Now which side we have been inserted the new node? The new node is inserted in the side of left. So you are going to take from the critical node, you are going to take the 3 nodes. So left, left. So from these things you are going to apply the LL rotation. So when you apply the LL rotation, then obviously this 36 will come here. Next 45 will go here. Next 27 will come here. The remaining nodes will not be changed. Now the 39. Where the 39 will go? 39 is greater than the 36. So obviously it comes to the right of 36 and compare with the node lies in the right subtree 45. So now compare 39 with 45. 39 is less than 45. So it comes to the left. So that is your certain tree. After doing the rotation, you are going to calculate the balance factor. Now when you are calculating the balance factor after doing the rotation, all the balance factor lies +1, -1 and 0. So there is no critical node available in this resultant tree. The same example I have been given for RR rotation. So RR rotation, here the critical node find here is 45. Here you are going to apply and you are going to change rotate the tree in the left. So I rotate the tree in the left. 63 will go up, 45 will come down. Again, along with the 63, all the child nodes will go. So 54, now the 63 becomes root. 54 will be there. So 54 will go to the any one of the child nodes in the left side. This is your LR rotation. So LR rotation, how you are finding out here? First, we will be having the tree like this. Now after inserting 37, the tree becomes unbalanced. Since the 45 getting the balance factor of 2, so you are going to apply the LR rotation. So where in which side we have been inserted this 37? 37 is inserted in the 37 is inserted in the left side. So we will be finding that LR rotation. So when you apply the rotation, you will be getting a resultant tree like this. Now we will be doing the insertion. So whenever you are doing the insertion, we need to follow some steps. So these are the steps you are going to follow. So first step, you are going to insert the new element in AVL tree by using the binary search tree logic. Next, after insertion, you are going to calculate the balance factor. Then the balance factor you are going to check whether it lies from -1, +1 or 0. And then if it is not lies in this range, +1, -1 or 0, then you will be doing the rotation. Now this is an example. So first we are inserting the element 63. So once you insert the element 63, you are calculating the balance factor. The balance factor is 0 since there is no left and no right. Next step 2. Step 2, I am going to insert the next element 9. So when you insert the next element to the AVL tree, again I am going to calculate the balance factor 0 and 1. So there is no critical node. When you come to the next step, insert the element 19. When you calculate the balance factor, you are getting the node called 63 is become critical. When any node becomes critical, then you identify the rotation. What type of rotation it is. Now the rotation I am identified here is the LR rotation. So you are going to perform the LR rotation and then you keep inserting the elements one by one with continuing the steps. So when you continue the steps, the final AVL tree will becomes like this. Next is the deletion. So how you will perform the deletion in the AVL tree? You will perform the deletion in the AVL tree as how you will perform the deletion in the binary search tree. So binary search tree will be having the 3 cases. Case 1 deletion, that is the node does not having the child. When the node does not having the child, then you delete the node as it is. Then case 2, when the node is having one child, then you will swap the elements, the child elements to the root node and the root node elements to the child node, and then you will delete as it is. Then you come to the third one. The third case is the node having the 2 children. When the node is having the 2 children, then either you can pick the element from the left subtree or from the right subtree. When you pick the node from the right subtree, then you are going to take the minimum element from the right subtree. When you pick the element from the left, then you are going to take the maximum element from the left subtree. And this is the case when you are doing the deletion in the binary search tree. Same case you are going to apply in the AVL tree also, but one more property you are going to do it here, that is you are going to check the balance factor. After doing deletion also you are going to check the balance factor for all the nodes. So in this balance factor, when you are checking the balance factor we already know that it should lies only with the values of 0, +1 and -1. If it goes beyond these values, then you are going to apply the rotation. Here you are going to apply the rotation in the form of 3 cases. Case 1A, B and C. So here when you are deleting from the right subtree, you will be following these cases. When you are deleting from the right subtree, you are going to check if any node having the balance factor of +2 and this left child is +1, then you are going to perform the LL rotation. This is not the case in the insertion. Now the rotation and the insertion deletion will getting vary. So kindly go through all these deletion before doing the problem in the AVL tree. So next case, when you do the BF node, that is the node which is identified as a critical node +2, then you are going to check the left child of the particular node is -1, then you are going to perform the LR rotation. Next case, when the node plus 2, that is the node which is critical, when you identify the left child is 0, then you are going to perform the LL rotation. So this is the case for deleting the node from the right subtree. In the previous slide, we have discussed about the deletion in the right subtree. Now this is the case for deleting the node from the left subtree. In deleting the node from the left subtree, the node which is identified is minus 2. In the right subtree, the case is plus 2. In the left subtree, it is minus 2. Only the 3 cases will be varying here. When the right child is minus 1, perform RR rotation. When the right child is plus 1, perform RL rotation. When the right child is 0, you are going to perform the RR rotation. So these are the rotations you are going to be memorized when you are doing the deletion operation in the AVL. So now we are going to discuss about the gate questions, which is the topic in AVL tree. So what is the first question? So which of the following is not the critical node in the given BST with the elements 12, 8, 18, 5, 11, 17, 4 and 2. So when you want to identify the given elements which is not a critical node, you just like that you see the elements and you cannot say that the options. So before choosing an option, you are going to create the binary search tree. So first you will be inserting the binary search tree 12. Since there is a no root node, you are going to consider the first node, always the first node as root node. So 12 is the root node. Now insert the next element 8. So 8 is less than 12. So obviously in the left. Now come to the next element 18. It is greater than 12. So come to the right. Next is 5. Now compare with the root element. 5 is less than 12. Less than 8, so come to the left. Now come to the 11, so 11 is less than 12, it is greater than 8, so come to the right. Next is 17, greater than 12, but it is less than 18, so come to the left. Next is 4, less than 12, less than 8, less than 5, so come to this side. Now it is 2. Again compare with the root element. 2 is less than 12, less than 8, less than 5. Again it is less than 4. So come to this side. So this is the way you will be constructing your given elements. This is your final list. Now the question is, which of the following is not the critical node? So there we given some nodes here. 12, 5, 11 and 18. So we want to find out either 12 is not the critical node, or 5 is not the critical node, or 11 is not the critical node, or 8 is not the critical node. So if you want to find out any node is not the critical node or any node which lies under the critical node, then you are going to be calculate the balance factor. So balance factor, what we discussed in the previous introduction about your AVL. So balance factor, how do you calculate the balance factor? You will be calculating the height of the left subtree and the height of the right subtree. So height of the left subtree, I already told that if it is a leaf node, the balance factor of all the leaf node is always 0. So put 0 for all the leaf nodes. Now calculate the balance factor of this. So there is no left, so only right, so minus 1. Here we have 2 left, so 2. Here again when you considering this 1, 2, 3, so 3 minus 1, it is 2. Here only 1 left, so 1. So what is the height of the left subtree? 1, 2, 3, 4. So 4 minus 2, it is 2. Now after calculating the balance factor, you can able to tell that what are all the nodes of in the critical stage and what are all the nodes in the non-critical stage. Now what is our option? Now check. A 12. 12 is not the critical node? No. 12 is a critical node. Since it has got the balance factor as 2. So this is not our option. Now come to 5. 5 we have got the balance factor is 2. So it is not the critical. It is a critical node. So we do not come in our option. Next C. Come to the 11. So 11, the balance factor what you got is 0. Since it is not the critical node. Now check 8. 8, the balance factor what you got is 2. It is critical node. So the option here is 11 is not the critical node. Next, dash number of rotations required to insert the sequence of elements 9, 6, 5, 8, 7, 10 into the empty AVL tree. So the tree is not given. You are going to construct the AVL tree. So whenever you are going to construct the AVL tree, the first element you are going to consider is a root node. So now construct your tree. So 9. Whenever you are inserting the new element into the AVL tree, always you are going to calculate the balance factor. No left, no right, so it is 0. Now insert the next one. 9. 6 is less than 9. So this side 6. So calculate the balance factor 0, 1. Now 5. The previous tree is 9, 6. 5 is less than 9, less than 6. So comes to the left. Now calculate the balance factor 0, 1, 2. Now you check the balance factor. 0 is okay, 1 is okay, 2 is not okay. Why 2 is not okay? It is not lies under the plus 1, 0 or minus 1. So now this is your critical node. Since it is a critical node, first you are going to identify rotation. What rotation you are going to perform? So what rotation it is? It is L rotation. If it is a LL rotation, then you are going to be rotate in right. So when you rotate in the right, you will be writing 6, 5 and 9. Now calculate the balance factor. Since it is a leaf node, 0, 0. For this, left is 1, right is 1. So 1 minus 1, 0. This is your AVL after inserting 9, 6, 5. Now insert 8. Compare 8 with the root node. It is greater. So come to the right. Now when you compare the 8 with 9, it is lesser. So it is left. So now calculate the balance factor. 0, 0. For this 1 and here 1 minus 2. It is minus 1. All the balance factor are okay. So no critical nodes. Now next you are going to insert 7. So when you insert 7, compare the 7 with 6, greater. So right. Compare 7 with 9, it is lesser. So come to 8. This side, left side. So compare the 7 with 8, again it is, you will insert here. Now calculate the balance factor. 0, 1, 2, 0. This 1 minus 1, 2, 3. Minus 2. Now check the balance factor of all the nodes. 0 okay, 1 okay, 0 okay, and 2 is not okay, and this minus 2 is also not okay. Now 2 nodes are critical when you insert the element 7. So when you insert the element 7, the 2 nodes become critical. Since it is having the balance factor of 2 minus 2, first you are going to identify the node at the bottom level. Now you are going to put the level. Is there any nodes identified in this level is critical? No. In this level? No. In this level? Yes. The one node becomes critical. So first you apply the rotation for that node. So when you apply the rotation, you are going to find out the rotation first. What type of rotation it is? It is L rotation. So if it is a LL rotation, you are going to rotate to the right. So when you rotate, you will be getting 6, 5, 8, 7 and 9. After rotating, you are going to again calculate the balance factor. 0, 0, 0, 0, 1 minus 2, it is minus 1. Now, all the nodes are having the balance factor which lies in the plus 1, minus 1 and 0. So, there is no critical node. So far, how many rotations we have been performed? 1 LL rotation, second rotation is LL. Next, we'll insert the next element 10. So when you insert the next element 10, compare with the root node. So when you compare the 10 with 6, it is greater. So come to the right. Already one node is there. Now compare. 10 is compared with 8, it is greater. Now come to the right. Now 10 is compared with 9, again it comes to the right. Calculate the balance factor. It is 0, minus 1, 0, 1 minus 2, it is minus 1, 0, and for this 1 minus 1, 2, 3. So 1 minus 3, it is minus 2. So now check the balance factor of all the nodes. 0 is okay, this 0 is okay, minus 1 is okay, and this minus 1 is also okay. Now the critical node is minus 2 here. So now you are going to apply the rotation. First you are going to find out what type of rotation it is. So what type of rotation? It is a rotation called RR rotation. Why I am telling it is a RR rotation? From the critical node you are going to identify the path. So the new element 10 is inserted at the right side. So you are going to identify the right path. So you are going to check RR rotation. So when you apply the RR rotation, you are going to rotate your tree in the left. So 8, 6, 5, 9 and 10. So where the 7 will go? Where the 7 will go? The 7 will go to the left. That is, when it goes to the left, 6 is there, 7 is greater than 6, so 7 will come here. Now calculate the balance factor. 0, 0, 0, 0, minus 1, 0. Now the third rotation we applied is RR rotation. So how many rotations we have been applied to insert the given sequence of element? That is 3 rotations. So the correct answer is 3. Now next question. Which of the following below diagram is following the AVL tree property? If it is a AVL tree property, you should always calculate the balance factor. After calculating the balance factor only, you can able to identify that the given tree is a balanced or not. Okay. For the given 2 trees, you are going to calculate the balance factor. When you calculate the balance factor for this, it is 0. It is 0, 0. For this 1, for this minus 1, and this 1, 2. This 2, and here 2 minus 1, 2, 3. 2 minus 3 minus 1. So the node which is here is having one critical node. Now come to the second diagram. So it is 0, 0, 0, 1, 0, 1, 2. So 2 minus 2 is 0. Here in the second diagram, none of the nodes are having the balance factor behind the plus 1, minus 1 or 0. So there is no critical nodes here. So obviously the second diagram is the following the AVL tree property. So the answer is C, only 2. So this is your last question. So what is the maximum height of any AVL tree with 7 nodes? Assume that the height of the tree with the single node is 0. So when you want to calculate the height of any AVL tree with the given nodes or the nodes are not given, you should use one formula. The formula here is n of n is equal to n of n minus 1 plus n of n minus 2 plus 1. With this given recurrence relation, they will be giving some assumption is n of 0 is always 1. When you apply this, for example, we will be having the levels n of 1 first level, n of 2 second level, n of 3 third level. If it is a n of 1, the first level, how many nodes will be there that you want to find out? You are going to apply this 1 in this formula. So n of 1 minus 1 plus n of 1 minus 2 plus 1. So you will be getting n of 0 plus n of minus 1 plus 1. So n of minus 1 will be not having the level. So obviously the n of minus 1 will be the 0. So n of 1, it is 1, 1 plus 1. So how many nodes will be available in the level of 1? The number of nodes available in the level of 1 is 2. So when you calculate like this for n of 2, so we have been find out that in the 0th level, the number of node is 1. In the first level, the number of node is 2. When you calculate for the next level. But how many nodes will be having in the level? 7 nodes. We didn't get it. So we will be going for the next level, n of 2. So n of 2 minus 1 plus n of 2 minus 2 plus 1. So n of 1 plus n of 0 plus 1. So n of 1, 2 plus n of 0, 1 plus 1. So how many nodes will be there in the second level? N of 2 will be 4. So still we didn't get the nodes. How many nodes we need to get? We need to get 7 nodes. So we will be calculating for the next level, n of 3. So n of 3, apply in this formula, n of 3 minus 1 plus n of 3 minus 2 plus 1. So n of 2 plus n of 1 plus 1. So n of 2, 4. N of 1, 2 plus 1. So we will be getting 7. N of 3 is equal to 7. So n of 3 is equal to 7. So what is our question? We are going to find out the maximum height of any AVL tree with 7 nodes. So when the AVL tree will be having the 7 nodes? When the AVL tree having with the height of 3. So the answer is 3. So these are the gate questions discussed under the concept of AVL tree. I hope you will be understand, and will be having any doubts. We'll be discussing few questions in the upcoming sessions. Thank you all.